Okay. So the first few are just kind of review from algebra. Again, probably maybe that's half this test or a little bit more, and then we start to get toward limits and derivatives at the end. So one is just, something that comes up a lot because, derivatives is based on the concept of rate of change in linear functions mixed with limits. So let's find the equation of the line that passes through 2 points. I wonder if I make this bigger, if that gives any more room. Never tried that. Yeah, well, looks all right for now. Passes through, let's pick 2 points, I don't know, say 1, 8, and I don't know, 3, 2. So the first thing you want to do here is find the slope. So you start by doing change in y over change in x. So I'm going to do 2 minus 8 divided by 3 minus 1. So I get negative 6 over 2, which comes out to negative 3. So I know my line has to look like y equals minus 3x plus some y-intercept value. And then I can just plug in either one of those points for x and y and solve for the missing letter b. So if I do that, I get 8 equals minus 3 times 1 plus b. So we're just adding 3 to both sides. And we get 11 as the value of b. So our line is y equals minus 3x plus 11. Number 2, we're going to look at some factoring problems. So 2, let's say, solve by factoring. So we'll do kind of a, let's say, easy one and a slightly more challenging one. So for A, let's say we have x squared plus 17x plus 72 equals 0. So when you have a trinomial like this and the leading coefficient's just 1, that's all you have to do is look at that last number, 72, and find 2 numbers that multiply to 72 but add to the middle coefficient, the coefficient of x, which is 17. So the numbers that do the trick are 8 and 9. So that means this factors into x plus 8 times x plus 9. And when you have 2 things that multiply to 0, one of them or the other one has to be 0. So x plus 8 equals 0, or x plus 9 equals 0. So solving those, you get x equals minus 8, or x equals minus 9. And those would be your 2 answers. B, let's try one where the leading coefficient isn't 1. Let's say, I don't know, let's say maybe 6x squared, say minus 11x minus 3 equals 0. So in this case, we can't just find the numbers immediately. We have to start by multiplying the first number, 6, with the last number, minus 3. So that gives us minus 18. So then we're looking for 2 numbers that multiply to minus 18. Oh, did I botch this up? Yeah, I messed up my signs here. So let's do, let me change the middle number. Apologies, I was just trying to do it on the fly and I added instead of subtracting. So let's make this minus 7x so the numbers actually work. So anyway, you still go through the same process. 6 times negative 3 gives minus 18. Now we want 2 numbers that multiply to minus 18 but add to that middle number, minus 7. So the signs are important here. So we know it's some combination of 2 and 9, But if you use positive 9 and negative 2, that would add up to positive 7. So we have to be sure that we use positive 2 and negative 9, because we know 2x minus 9x is minus 7x. And that's essentially what we're going to be replacing the minus 7x with, so that we can factor by grouping. So the next line down, we write 6x squared plus 2x minus 9x minus 3 equals 0. And then we pair the first two, 6x squared and 2x, and we pair the second two, minus 9x and minus 3, and we take the greatest common factor out of each pair. So we can take 2x out of 6x squared plus 2x, and 3x times 2x makes 6x squared, and 1 times 2x will make 2x. And then in order to get a matching 3x plus 1 in parentheses, we just need to take minus 3 out of the minus 9x minus 3. So if you take out a minus 3, we'll get 3x plus 1. And then we get the full factorization, 2x minus 3 times 3x plus 1. And you just set each one equal to 0 and solve. So 2x minus 3 equals 0, or 3x plus 1 equals 0. So we get x equals 3 over 2, or x is minus 1/3. That's it for number 2, factoring. Another one that we want to do, we saw that if we knew an exponential function behaved, or if we knew some data was behaving exponentially, and we had 2 of the points, we could actually find the exponential function as well. So that's number 3. Find the exponential function. That passes through let me kind of reverse engineer this. So on the other review, the other video I have, I believe I gave you the y-intercept. So I'll do one here where you don't have the y-intercept. So let's say 1, 5 and 4, 16.875. So what we want to do here is just remember the standard form of an exponential function is something like y equals ab to the t, and then plug in your coordinates. So t would be the first coordinate, y would be the second coordinate. And remember, I like to plug in the one with a larger t value first. So I would have 16.875 replacing y, and then 4 replacing t, so I get ab to the 4th. And then in the other pair, I would have 5 is equal to ab to the 1st. And the whole reason is we can take ratios. If these things if both equations are equal, if I divide both sides, I will have an equation as well. And by dividing ab to the 4th over ab to the 1st, what will happen is a will be eliminated, and I'll have an equation only in b. So I can say 16.875, that fraction divided by 5 is equal to ab to the 4th over ab to the 1st. Right, so the a's cancel, and with the b's, you subtract the exponents. So 16.875 divided by 5 is 3.375, and that will equal b to the 3rd power. So to undo the 3rd power, what you do is you either take the 3rd root or the 1/3 power of both sides. So we'll take the 1/3 power of both sides. So on the one side we get b, on the other side we get 1.5. So now we know our equation looks like y equals a times 1.5 to the t. So what we want to do is we want to just plug in one of our 2 points and solve for a. So let's plug in 1 and 5. So 5 equals a times 1.5 to the first power. So we just need to divide on both sides by 1.5. And we get our value of a, which is 3.3 repeating. Or you can convert that to a fraction as well. So that would be 3 1/3, or 10/3. Either way. So you could either write it as, y equals 3.3 repeating times 1.5 to the t, or you could do it with fractions. Y equals 10/3 times 3/2 to the t. Either way. Okay, so we've got one where we've got some log properties. So let's say write as a single logarithm. You could also talk about expanding. Either way, your log properties can be used to either condense them or kind of expand them, so long as their bases match. So let's say we have 7 common log of x plus 2 times common log of y minus, let's say, 3 log of z. So we had essentially 3 log properties. That we're making use of. One, if you have log of m plus log of n, you can write this as the single logarithm log of m times n. 2 log of m minus the log of n can be written as the log of m over n, and 3, if you had the log of, say, m to the p power, you can bring the p out front and write that as p times the log of m. So the thing is, we can't use property 1 or property 2 if there's anything sitting in front of the logarithm. So that's where property 3 comes in. We want to take all those coefficients that are out front and put them back inside. So I start with property 3. So I have the log of x to the 7th plus the log of y squared minus the log of z to the 3rd power. And now that's where we're going to be able to write this as a single logarithm. I can multiply the x squared by the x to the 7th by the y squared, and then divide by the z cubed. So I get the log of x to the 7th y squared over z cubed. And that's it for number 4 here. Okay, so then we actually go ahead and use the log to solve some exponential equations. So I did one with e on the other review, so let's do one with 10 here. So we kind of did the natural log on the other review, so we'll do the common log here. So solve for x. Let's say we have 3 to the 4x minus 1, and that's equal to 10 to the, let's say, 7x. So the thing is, what we want to do is use those properties before, but realize that the common log will cancel with any exponential expression where 10 is its base. So we want to take the common log of both sides here. So that's where we start. We start with the log of 3 to the 4x minus 1, and that will equal the log of 10 to the 7x So on the right, we get that cancellation we were looking for. And on the left, we want to bring the exponent down in front. So we have 4x minus 1 times the log of 3. And then if they allow you to use a decimal answer, the easiest way I would tell most students is to just go ahead and plug the log of 3 in your calculator. So, and you know, round that to a few places. So I'm going to do that here. So we get log of 4x minus 1 times 0.477, and that'll equal 7x. And then just solve the remaining linear equation. So multiply your 0.477 through. So 0.477 times 4 is 1.908x minus 0.477. And that equals 7x. So we want to move the 1.908x to the other side to collect our x's on the same side of the equation and leave the other number, the minus 0.477, alone. So on the left, we just have the minus 0.477. And on the right, we'll have 5.092x. And then we just want to divide by that 5.092 to get x by itself. So x here will be about something like minus 0.094, something like that. And again, that's an approximation since we rounded the log of 3. If you don't want to round, you need to leave everything, the log of 3 in the problem, till the end. But I found in the past students get more confused by that, so I usually just use the rounded version. Since this is an applied class, usually we're dealing with rounded answers. Okay, 6, I'm going to do the same problem, but again, I'm just going to switch the numbers. So suppose, are there any questions? Feel free to jump in if you have a question. Okay, so for this one, we've got a population of a bacteria colony measured in thousands after T hours, and it's given by a model. So let's say P of T, and let's change it up a little bit. So let's say it's 4.2 times e to the 0.3t. So we have an exponential function in continuous form. So we just want to find and interpret the ARC, the average rate of change. So one thing to remember when we're doing the average rate of change, the units of it are going to be units of y per units of x. So when we're talking about this problem, the unit should be the bacterial growth in thousands of bacteria per hour. That's going to be the interpretation over this time interval. So say 1 to 3 hours. So to find the average rate of change, we first need to plug in the numbers, P of 3. So we get 4.2 times e to the 0.3 times 3. And, we'll get a decimal there. So we get something like 10.33. And P of 1 would just be 4.2 times e to the 0.3. So it comes out to 5.67. So then our average rate of change, so the ARC, is just the slope formula between these two things, which would be, let's say, 10.33 the y value minus 5.67, the other y value, divided by the two x values. Subtracted 3 minus 1. So 10.33 minus 5.67 divided by 2 comes out to 2.33. And as mentioned, this is going to be thousands of bacteria per hour. So we could say on average from 1 to 3 hours after the experiment began, bacteria increased by 2.33 thousand per hour. Okay, number 7 is a graphical limit problem where we have some one-sided limits and other features. So let's do something similar. Let me make a reasonable graph here. So let's make 2 like our interesting point. So we've got some curve that's coming from here. And maybe it actually occurs here, and then we have, and all this is just unit scale. So yeah, we'll come down to here. And then maybe we are doing this, I don't know, straight line, something like that. Okay, so this is, our function, let's say f of x, and we just want to evaluate based on this picture a few limits. So let's say evaluate let's say the limit as x approaches 2 from the right. So what you want to do is you want to find 2, the x value. So that's where this dot is. So this is 2 right here. And we basically want to be on the curve and follow the curve as we're approaching 2 from the right. So if you're doing that, you're on this line down here, then you jump up from this open dot to this closed dot, and then you're approaching this dot. Remember, it's not about where the graph is at 2, it's about where it looks like it's going from the right. So from the right, it looks like it's traveling to the highest open dot there at 3. So for that reason, we would say the limit as f of x approaches 2 from the right is 3. Now, on the other hand, what if we approach from the other side? Let's say we had the limit as x approached 2, but from the left. Well, then you'd be following this curve on the bottom, going to this lowest open dot. It would be traveling toward 2 from the left from this bottom curve, and it looks like it's going to that dot, and that dot has a y value of -2. So from the left-hand side, the graph would have a limit of -2. And then if you talked about the two-sided limit, remember the two-sided limit only exists if the left and the right limits agree with each other. So because they disagree, for that reason, the two-sided limit does not exist. But, you could actually talk about what happens if you evaluate the function. If you evaluate the function at 2, if you just plug 2 into the function, you get that dot that is on the x-axis right at 2, and that has a y value of 0. So the one-sided limits talk about where it's approaching from the left and coming from the right, and then the two-sided would be the same if it existed, but in this case it doesn't. Okay, then from there we've got some derivative questions. So we've got just one by the definition and then a couple of shortcuts. So remember the definition. So compute using the definition. Let's say compute the derivative. This. So let's say f of x, we're just going to do something that's kind of a simple polynomial, maybe 7x squared plus 3. Now, using shortcuts, we already know what this derivative should be, so you should have that answer in mind. That way, if it doesn't come out to that, you can go back and check your mistakes. So we know the derivative should just be 14x. The derivative of x squared is 2x. 2x times 7 is 14x. And the derivative of a constant by itself, that plus 3, just becomes 0. So we should be wanting to see an answer of 14x at the end. So the definition, remember, f prime of x is given by the limit as h approaches 0 of f of x plus h minus f of x over h. This is just the general definition. So if we plug that in, we would have 7 times x plus h squared plus 3, and then we would subtract f of x, which is 7x squared plus 3. I forgot my limits, so I'm going to have to squeeze that in over h. So let me try and squeeze that in a bit better. So this is the limit as h approaches 0. So then I want to expand. So the first thing, we want to multiply x plus h by x plus h. And we do that using FOIL. So we would have 7 times x squared plus 2xh plus h squared plus 3. And then we have minus 7x squared minus 3 from distributing the negative sign across the second set of parentheses. So if you look at that, the plus 3 and the minus 3 will drop out. They'll cancel. And then that's all we have to do is distribute that 7 across the second set of parentheses. And you might already see that the 7x squareds are going to be set up to cancel as well. We have 7x squared plus 14xh plus 7h squared minus 7x squared. So the plus 7x squared minus 7x squared drop out. And then the last thing we need to do is just factor out an h on top. Remember, the goal is to cancel that h in the denominator. That's what's preventing us from evaluating the limit. So when you take out the h, we'll get 14x plus 7h. And this is what cancels with the h in the bottom. And so then, since you've canceled that h, now we're allowed to plug in the h. We're allowed to plug in 0 for h for any remaining h's. So that would be 14x plus 7 times 0. So that other term vanishes as well. So we just end up with 14x. So then the last two, we just want to do derivatives using shortcuts. So are there any questions on that one? It's maybe the trickiest problem in terms of just number of steps. So let's say number 9, just find the derivative. So you don't have to use the definition, you can just use the shortcut rules. So let's say we have f of x is 12x to the 4th minus 6x plus pi. So the derivative here, f prime of x, we just go term by term. So the derivative of x to the 4th is 4x cubed. So we'd have 12 times 4x cubed minus 6. And then remember, the derivative of pi is actually 0. So we would just end up with the derivative of 48x cubed minus 6. And that's it for number 9. And then number 10, we'll do another one where we find the derivative. let's say we have g of x as, I don't know, maybe 13x cubed minus 1 over x squared. So the trick here is to first rewrite the g of x by using the common denominator and splitting it up into two terms. We don't have any rule for taking derivatives of quotients yet. We will learn the quotient rule in the near future, but it's not necessary here if we use algebra. So we have g of x can be rewritten as 13x squared, 13x cubed over x squared. Minus 1 over x squared. So this is 13x, and then remember, if we want to take the derivative, we want to try and write it as x to a power. We don't want to be dividing, so 1 over x squared is the same as x to the negative second power. And then from there, we can take the derivative. So g prime of x, the derivative of 13x is just 13. And then for the other one, remember, we bring the power down, so we have minus 2x, and then we subtract 1 from the power. So negative 2 minus 1 is going to be minus 3. So we end up with 13 plus 2x to the negative 3, or 13 plus 2 over x cubed, if you want to rewrite it using the fractional notation that we started with. But essentially that's it. Split it up into two terms and then take the derivative using the rules you already know. So yeah. Let's take this out of full screen. Okay. So let me end the recording here.